would like to talk to you about simplifying expressions that have a fractional exponent that's rational. And what I mean by that is the exponent is a fraction made of integers. The denominator can't be 0. But before I do that, I would like to do a little history lesson about a man named Pythagoras. Now, I've already mentioned his theorem in earlier lessons. It's a squared plus b squared equals c squared, standing for the sides of a right triangle. So you can square one side and add it to the square of the other side, and it equals the square of the third side. Now, the Pythagoreans liked everything neat and orderly. But when they looked at a right triangle like this, with a base of 1 and a height of 1, and applied their theorem, they got the square root of 2 for the other side. Now, the square root of 2 is an irrational number. You can't multiply any number times itself and get 2. And that's what you're asking when you ask for the square root of 2. Square root of 2 then is an irrational number. It's said that there was a guy that was a proponent of irrational numbers, and he mysteriously disappeared. Now, our simplified expressions may be irrational, but our exponents are rational. Okay, let's look at this first definition. And what does this mean? A to the 1 over n, where a is a number greater than 0 and n is a positive integer. Let's take an example here. 100 to the 1/2. Now, what we can do is put the 1 with the 100 and the 2 with the radical sign. But by convention, we can just say the square root of 100 and forget about the 2 out front there. And the square root of 100 is asking what number times itself equals 100. It's 10. So let's look at another example. 8 to the 2/3 equals, put the 2 with the 8 and the 3 with the radical sign, and so you get the cube root of 64. That's asking what number times itself 3 times equals 64, and that would happen to be 4. So a to the 1 over n is called the nth root of a. So let's look at another definition here. A to the m over n. Now, by using our rules of exponents, we can bring the m outside the parentheses there. M and m are positive integers, and a to the 1 over n is a real number. So let's try this out and see if it works. 4 to the 3/2, so let's pull out the 3. That means to cube 4 and to the 1/2. Now, judging by what I've just talked about, 4 to the 1/2 is the square root of 4. So you have the square root of 4 times itself 3 times, which gives 2 times itself 3 times. And it equals 8. Now, just for fun, let's go back and use the previous definition and see if we get the same answer. 4 to the 3/2, you put the 3 with the 4 and the 2 with the radical sign. So it's asking for the square root of 64. So what number times itself equals 64 is 8. So 8 equals 8. So they jive there. Next problem, 9 to the 3/2. So the 3 goes with the 9 and the 2 goes with the radical sign. Now, we get 9 cubed under the radical there. Let's look at just the 9. Here's a way of working this. 9 is 3 squared. So we got 3 squared cubed. Now that means that you multiply 3 squared times itself 3 times. And so we'll get, or we can get the square root of 9 times 9 times 9. We can multiply 2 9s together and get 9 squared. Now, using a rule of radicals, you can pull those apart. Then you're going to get the square root of 9 squared times the square root of 9. The square root of 9 squared is 9, and the square root of 9 is 3. and 9 times 3 is 27. So let's see what our next problem here. 27 to the 2/3. Put the 2 with the 27 and the 3 with the radical sign. So we get the cube root of 27 squared. Here's a way of working this. Look at the 27. 27 is 3 cubed. Now square that, and that is just 3 to the 6th. Now we have the cube root of 3 to the 6th. 3 to the 6th means 3 squared times 3 squared times 3 squared, or 9 times 9 times 9. So we can pull out a 9. That's the cube root of all that. All right, next problem here. Now we have a negative exponent. So this is a little bit different. If you have a negative exponent like this, then you can change that to a positive exponent if we move it to the denominator of a fraction that has a numerator of 1. So in the denominator of this, we have the square root of 25 over 49, which comes out to be 5/7. Now let's multiply 7/5 times the numerator and denominator to clear this up a bit. So the denominator becomes 1, and then you're just left with 7/5. So that's something we can do with a negative exponent. Now here is a situation where we have like terms. If you have like terms and you're multiplying together with their exponents, the rule is that you can add the exponents. And so we add negative 1/4 plus 3/4, and we get y to the 2/4, and that reduces down to y to the 1/2. And judging by what we've said earlier here, y to the 1/2 can be the square root of y. So those are reduced forms of our original problem. Again, here we have a situation with a negative exponent in the denominator. If we move that to the numerator, we can change that to a positive 5/6 and then multiply that times y to the 2/3, and so we get a situation where we're adding exponents again. So we get y to the 2/3 plus 5/6. Now we got to get the denominators the same. Use the least common multiple, and it comes out to be 6. And so we can add 4/6 and 5/6 together, and we get 9/6. That reduces down to 3/2. And this could be put another way as the square root of y cubed. Now, this last problem here, you got to be careful. Okay, we have a situation with a negative exponent again. We can move that to the denominator of a fraction whose numerator is 1, and the exponent becomes a positive. So that becomes in the denominator the square root of negative 2 to the 5th. Now that means negative 2 times itself 5 times, which gives us the square root of negative 32, which is, we have a negative under the radical. It's not a real number, it's an imaginary number. Thank you.